Okay, so what I want to look at today we're gonna, one of 2 days we're gonna spend on chapter 8. Chapter 8 is really cool stuff, really important stuff, but it's not very hard. You're gonna see this a lot more next year, but in preparation for the compass test, I want you to have an introduction to this. So, exponential and logarithmic functions. Let's look at exponential functions first. And I'm going to focus on the graphs of exponential functions first. And then we'll start looking at how we can actually, some of the properties of these functions as well. So if we write exponential functions, we're going to start off, we're going to write
right behind you.
Whoops. So if we write exponential functions in their general form, first of all, and then we can just figure out, like for example, this would be equivalent to writing a cube root function as, we might write it as y equals a times cube root of x minus h plus k, for example, right? And if we just know the values of a, h, and k, we know what the graph looks like. The same kind of thing is true for exponential functions. For exponential functions, they're in the form y equals a times b to the x. Okay, and I want to make sure I'm using the different books use different forms of this. I want to make sure I'm using exactly the form that this book uses. And I gotta check one thing out just to make sure. Yes.
So wants me to go as soon as convenient, so I don't know when.
I'd hold off a little bit. All right. Yeah. Okay, so they look like that. All right. Now notice that this is a little different than what we're used to. Notice that we're used to things like with polynomials, we're used to the variable being the base and having integers, or maybe not even integers. We could even have like rational exponents in chapter 7, but the numbers are the exponent. This is backwards. This is giving us a constant for the base, and the variable is the exponent, right? So if we want to look at what the graph of this thing is going to look like, let's just take a quick look at this. So if we're going to graph this on the xy plane, what would happen? Let's first of all see what would happen if x were 0. If x were 0, what's going to happen to that function? A times, John? 1. How come?
The zero power except the 0 is 1.
The 0, okay, 0 exponent property. Anything to the 0 power equals 1, right? So if we plug in 0 for x, we're going to get back the value a times 1, so we just get back a, right? So one point we're going to have is through the y-intercept is going to be at 0, a, right? Now what's going to happen after that? Let's say x equals 1. What are we going to get? A times b, right? So we're going to go over here. We don't know what a, we'll put in some numbers in a second, but if we go over to x equals 1, we're going to go up to a times b. So let's just pretend it's right there.
So a would be like x and 0, or a would be minus 0 would be like x.
A would be, well, a, they're both going to be numbers.
Oh.
Both going to be numbers. These are just going to be constants. Okay? But now I want you to see what happens to the shape of this thing. As we go over to x equals 2, what's going to happen?
A squared times b squared.
No. A times b squared. You see what's going on? That's going to make this thing grow really rapidly, isn't it? Right? And so the next point's going to be way up here somewhere, right? Every time x increases by 1, we're multiplying by an additional factor of b, aren't we? Does that make sense? Okay, so for that reason, we recognize that b is what we call the constant multiplier. Because each time we increase by the independent variable, or x, by 1, we are gonna multiply the value of the function by b. So it grows extremely rapidly then, right? This is what, exponential growth is very rapid growth. A is what? What do you think A is? A was important to us at this point right there.
The y-intercept.
Okay, it's the y-intercept. Another way of thinking of that is when x is 0, that's the value of y, isn't it? So a lot of times we call that the initial value. Okay, in other words, initial means when we're starting. When x is 0, what's the value of the function? In this case, it corresponds to the y-intercept, but if I were to connect the dots on this thing, so to speak, I would get a function that looks like that. Starts with slow growth when we get negative values of x. And let's look at that for a second. If I were to backtrack a little bit and go back to x equals -1, what do we get? A times b to the -1. What is b to the -1?
So it's
A divided by b. So that's giving us a much smaller number, isn't it? Right? When I divide by something, I'm making it smaller, right? Unless I'm dividing by a fraction. Okay, when I go back to -2, now I've got a divided by b squared. So I'm dividing by an even bigger number, and if I get a big number on the bottom, right, if I look at this point, oops, if I look at this point right here, I get -2 a over b squared, right? As the bottom of a fraction gets bigger, what happens to the size of the fraction? Gets smaller. And so do you see that if I were to backtrack and move in the negative direction, I'm just gonna keep getting fractions of a, right, that are gonna be smaller and smaller and smaller fractions of a. What number am I approaching? If I go way out here to x equals -100, for example. I'm approaching 0, aren't I? If I go back to -100, I would be at the point -100 a over b to the 100, or a times b to the -100, same thing, right? Now that's could be a very, very large number on the bottom, but it's still just a big number. I still have a on top. Do I ever actually get to 0? I never do I? So we'd say then that the x-axis here is an asymptote. We're always, as we move off to the left, we're always going to approach that axis, but never quite hit it, okay? As I scoot to the right, things keep increasing more and more rapidly. It starts off pretty modest because these are fractions, right? But once we get up to here, things really pick up steam. Okay? Every time I scoot to the right by 1, my constant multiplier is really increasing things dramatically. Okay? Yep. Question? It doesn't reach 0 because even if I went back to like -1,000,000, for example, I'm still going to get a divided by b to the 1,000,000. I always get, I get a really small fraction, but the only way I could ever get 0 for a fraction is if the top were 0, and it's not, right? Okay, yes?
I'm a little bit confused for like what a equals.
Okay, I think it's helpful. Let's look at a numerical example. I think that really helps if we look at an example with numbers in it. So how about if we try this one? Let's sketch a graph, and then I'll show you a couple Moodle problems, what you'll be doing on Moodle. Let's sketch a graph of y equals 2 to the x. Now if we compare that to
So here's 1.
y equals a times b to the x, what are the values of a, b, and b here? A is 1, isn't it?
Yeah.
Because that's the number that's being multiplied by the power, right?
So we could, yeah, right.
So A is 1, what's B?
2.
2. Okay, so what A represents then? We said A is the y-intercept, right? That's the initial value. So if I were to sketch this thing, I know that it's going through the point 0A, so it goes through the point 0, 1, okay? B is 2, what does that mean?
That's how much.
What you're squaring.
It's what I'm multiplying by every time I scoot to the right. B is the constant multiplier. So if I scoot to the right by 1, if I started at 1, what's my next value got to be? 2. Yeah, 1 times 2, right? So my next value is going to be there. If I scoot to the right one more, what do I get?
4.
2 times 2, which is 4. Scoot to the right one more, 8. See how that goes? If I scoot back one,
2.
if I scoot back one, I'm getting 1 times 2 to the negative 1, right? That's 1/2. Everybody see that? So that's going to be there. If I scoot back one more, I get 1/2 divided by 2, right? Which is 1/4. See how that works?
So we're gonna
And
get
so,
really low, but not quite.
Once again, I get this exponential behavior. Okay?
So we're just gonna look almost perfectly flat until all this.
Yeah, it's asymptotic. So it looks, if you go far to the left, it looks very flat. Yeah. Okay? So what happens then? Here's the next question. So as A increases, A is like the coefficient we've always had. When we multiply by an A value that's big, don't we just stretch the whole thing, right? So if I change this to something like, let's say 3 times 2 to the x, what have I done? Well, now my original x-intercept is at 3. I'm multiplying 3 by 2, so I'm going to go clear up to 9. What did I do? I just stretched everything up by a factor of 3, didn't I?
3 times 2 equals 9.
Whoops, 3 times 2 is 6, sorry. Yeah,
It's Friday.
it is Friday, there we go. So 3 times 2 would be 6, so we'd be right up there. There we go. And then when I go out to 2, I'm going to do 6 times 3, which is 18, which is, 6 times 2 is 12. God, I can't think. 6 times 2 is 12, which is probably about right there, right? So what's going on here? This thing is a much steeper graph. How much steeper? 3. Everything's increased by 3 because now everything got multiplied by 3, right?
So it just goes up 3 every time.
So this is going to be 3 times higher than that. This is 3 times higher than that. This is 3 times higher than that.
So you just take all your, so if I wanted you to increase it, you can just take the points.
So one way we can do it is we can increase the initial value. If we increase the initial value to a bigger number, we're effectively just stretching it by that value, just like we've always done, right? When we multiply a function by a number, and the function is 2 to the x, right? That's the exponential function. If we multiply that by some number, we're just stretching it, or I could shrink it. If I multiply it by a number that was like 1/2, for example. Okay, yes? Oh, you had a question,
Oh,
Jay?
yeah. So, what would it look like if it was going down?
Okay, good. So now, what about that? So now, let's look at a different case. Let's look at a case next to this. We'll graph it in how about purple? Let's look at one where we have something like y equals 1/2 to the x. Okay, what's that going to do? What's our initial value? 1, right? Does everybody agree A is 1? So A equals 1. Our constant multiplier is 1/2. So this one is going to start at 1. And when I scoot to the right one, I multiply that by, so it goes down to 1/2. Okay? I go forward again, it's 1/4.
Oh, so it's just gonna be opposite.
Yes, it is.
So can it ever go down?
Yeah. Oh, yeah, we'll do that too. Yeah.
What happens if it's
Okay, well,
Yeah.
look.
Because wouldn't it
If-
kind of go up and down?
Okay,
Because
now if B can't be negative. B can't, because if B's negative, it
It'll go up and
oscillates and
down.
B can't be negative, but A could. We'll look at that case next. Okay, B has to be greater than 0, but the cutoff,
Oh, but if B.
kind of the threshold
Okay.
is B greater than 1 or less than 1.
Wait,
right?
so what would it be if it was like a negative half?
If B was,
A was.
oh, if A was, we'll look at that next.
Okay.
Yeah, we'll look at that next.
And you multiply it by
Okay,
negative.
let's finish this one up first. I want you to see what that does. Okay, if the constant multiplier is less than 1, then that means I'm multiplying each time by a fraction less than 1, so I'm reducing the overall size, right? Now, what if I backtrack though? What if I go back to -1?
Then it's gonna go up.
Yeah, if I take this to -1, then I've got 1/2 to the -1. What's 1/2 to the -1? 2, right? So when I go backwards, it's going up. If I go back one more to -2, I've got 1/2 to the -2. What's 1/2 to the -2? 4, isn't it? Because 1/2 to the -2 is the same thing. Remember with a fraction, it's the reciprocal, right? That's the same thing as 2 to the positive 2, right? So that goes up to 4, and what do you notice?
It's 16.
They're just reflections around the y-axis, aren't they? Okay. That make sense?
And
Okay.
so I think if it's, I'm just gonna throw my theory out here. So if A is negative, then you multiply the points by, say, if it was -1, then it would go down. You would multiply it by -1, so it would be below the
Okay.
x-axis.
Yes. Now, I want to consider one more example, and this is going to be a quick one. What would it look like if we took something like, on the same graph, it's getting a little bit busy here, but let me just erase about some of this stuff. Okay, we'll do this in green. What if we looked at y equals something like 3 times 1 to the x? Now, why is that just nonsense?
It's just
Isn't
one.
it just one?
Yeah, 1 to any power is what? 1. Okay, John.
It's so none of these graphs are ever gonna go through like 3 quadrants.
No. Nope. Well, yes.
You can.
I will-
So you can get it to start like at negative and go up.
I'll show you how. Now, that's a weird one. It's no and yes. Yes, we can technically do it, but there's a tricky reason why. You'll see why. I'll get there. Yep. Okay. So now if I graph this one though in green, this is just y equals 3 times 1. Well, that's not exponential, right? So my point is, the constant multiplier can't be 1. It either has to be greater than 1 or less than 1. And when it's greater than 1, we get something like this. That's what we call exponential growth for obvious reasons. The function is growing, right? So the red example where b is greater than 1 gives us exponential growth, okay? The purple example where b is less than 1 gives us exponential, what we call decay. Decay in math means something is decreasing, okay? The function's decreasing, okay? Make sense? Okay, next issue. What happens, now tell me what happens with this. What if we want to sketch something like y equals -3 times 2 to the x? Yeah, think what that does. If we multiply a function by a negative, what does that do?
Make it negative.
It reflects it over the x-axis, doesn't it? Right? And so the same rules still apply. What's a in this case? -3. Good. Okay. And b is, the constant multiplier is? 2. Okay, good. Good. So then we know that if we graph this guy, it's going to have a y-intercept of -3, right? And a constant multiplier of +2. So if I go 1 to the right, I'm going to get what? -6. I'm going to get -3 times 2 to the 1, so times 2, -6. So it's right there. If I go 1 more to the right, I get -3 times 2 squared, -12, right? So it's way down here somewhere. See how that works? All we've done is just flip it over the x-axis, right?
And then to make it go the other way, you do like -1/3 or something.
Yeah, exactly. Yep. If we wanted to graph, for example, let's say we wanted to do y equals -3 times 1/2 to the x, right? That's gonna look like this. Okay. Yes.
So, you said it could be in like 3 quadrants.
Okay. How do we do
but
that?
It never reaches 0.
You're right. You're right. Except, look what we can do here. We can do one other thing. What if you tell me, you're gonna know the answer to this, but I want you to tell me here. What's gonna happen if we graph? I'll give you a specific example first, and then we'll generalize this. So what if we're gonna sketch y equals, we'll just do 1 for a this time. 2 to the x minus 1
That's cheating.
minus 2. Okay, what do you think that does?
Decides reality.
What's it do? What?
Goes into quadrants.
Okay, yeah, what is the minus 1? If I subtract 1 from x in a function, what's it do? Scoots it,
To the left.
no.
Right.
Scoots it right,
Right.
right? Does that make sense? Just like it always did. With parabolas, with absolute value functions, with anything, the number that we subtract from x we call h, right? And that's always going to be the coordinate of the special point, which for us we'll take to be the starting point, right? Okay.
Right.
Another way of
So-
thinking about it is we've translated it 1 to the right. What does subtracting 2 from the whole thing do? Yeah, then k, that's plus k, right? So k is negative 2. Does everybody see that?
So we're gonna
This
go
is
down.
like saying, this is like plugging in values into y equals a times b to the x minus h plus k. It's like picking values, h k equals 1, negative 2, right? So what does that correspond to? Well, it corresponds to the graph of y equals 2 to the x translated like that. Okay, so let's graph it in light blue first, and then we'll translate it to get the final result. So what's that going to look like? This is it. We've done this one, right? This, what's a? 1. Okay, so then it's going to be, it's going to go through the point 0, 1. Scoot over 1, it's going to double. Scoot over 1, it's going to double. And so we get something like, basically like that, right? But what do we have to do?
The right one and down to 2.
Yeah, we got to go right 1 and down 2. So let's take this point. It's going to go this way 1, and it's going to go that way 2. So that point ends up there, right? The asymptote now, instead of being the line, the x-axis, what's our asymptote?
The formula or the.
What's this minus 2 for k do? Brings the whole thing down by 2, and so now our asymptote looks like this, right? It's the line y equals negative 2. Okay, and so our graph now looks like this. Whoops, maybe not quite. You get the idea.
Yeah.
I didn't draw that very well, but it'd be more like that kind of, right? I mean, you get the idea.
Yeah.
Right?
So it changes from not, it can't be 0 to it can't be negative 2.
Right.
So
Well, a still. What do you mean? It can't be 0. What do you mean?
Because you said it'll never reach 0 in the first.
Right.
So this one will never reach negative 2.
Exactly. Because, and here's a way to think about that. This part right here will never reach 0.
So the thing it'll never reach 0.
It'll never reach
doesn't
0
always-
minus 2, which means never. The whole thing never reaches negative 2.
Okay.
I really think the best way to think about these, and as you work with them more, next year you'll work with these a lot. As you work with them more and more, you get a good feel for them. But I think a good way to think about them is to always look at the base graph translated. Okay? Make sense?
Do you want me to go to my thing?
Whenever you feel like you need to. I'm gonna. It's up to you.
It'll probably be really quick.
Okay. All right. So that's in a nutshell. That is how we sketch graphs or recognize graphs of exponential functions. Okay. What I want to look at next, and we've had a lot of practice with exponential functions. You guys you've used your properties of exponents. You're very good at it. I want to introduce a new kind of animal here that goes with them, which is really powerful. So hold on to your hats. We're going to look at right here. Okay. Okay, so logarithms. Now, what do logarithms do? This is really a cool problem that they solve. Think about this for a second. We know that 2 squared is 4 and 2 cubed is 8, right? But what if we want to answer the question 2 to what power, call it y, is 6? How do you do that? Okay? There's a very powerful function in math that allows us to do that, that allows us to manipulate exponential equations and make them easier to deal with algebraically. Going into this, we use this stuff a lot in calculus, for example. One of the things I always tell my calculus students is logarithms make arithmetic easier. What they effectively do, and we'll talk about this more today, is if you think about the levels of complexity of arithmetic operations, the easiest are adding and subtracting, right? Harder yet would be multiplying and dividing. Harder yet would be exponentiating, taking things to exponents, right? What logarithms do, the properties of logs, and we'll get to this kind of at the end of the day, allow us to move everything down one rung on that ladder, make things easier to deal with. So for example, using properties of logarithms allows us to take exponential relationships and make those products or quotients, right? Which is easier, all right? So how does this work? All right, so because 6 is between 2 squared and 2 cubed, we know that we're going to get the exponent here. Y has got to be some value between 2 and 3, right? Okay, what's it going to be though? All right, to answer this, we use logarithms. Here's the definition of a logarithm. If a and x are positive numbers and a is not equal to 1, then we say that the base a logarithm of x is defined like this. If the base a logarithm of x is equal to y, this means if and only if. It's like a two-way arrow. That is exactly equivalent to saying a to the y equals x. Here's how I remember this. I always think of the statement, a logarithm is an exponent, or a log is an exponent, right? That might confuse some people in the timber industry, but what I mean by that is, when I say a log is an exponent, if I take a logarithmic equation and I rewrite it as an exponential equation, whatever the log was equal to, that becomes the exponent, okay? The base of the logarithm becomes the base of the exponential expression, okay? So let's take an example. So if we want to, for example, if we want to rewrite this in a way where we could make sense of this, we want to say, okay, the log of the base 3 log of 9 equals x. How do I rewrite that as an exponential statement? What's the base of the logarithm? 3, right? So that becomes the base of the exponential statement. A log equals an exponent. So 3 to the x equals 9. Yeah, exactly. Okay, so what's the answer then? 2, right? Does that make sense? You get how we do that? Because 3 to the x equals 9, well, solve that. So to yourself, you're thinking, okay, so 3 to what power? 3 to what equals 9? 2. That's the answer. Okay. When it's convenient, that's easy to do. If it's not convenient, the calculator tells us by using this logarithm operation, right? So we could ask, if we want to know, what were we doing? 2 to what power is 6, right? That's the original question we were answering. 2 to what power equals 6? How can I turn that into a logarithmic statement? What's the base of the exponential? 2. So that must be the base of the log.
Log 2, 6 equals x.
Okay, and remember that the log is equal to the exponent, right? So it must be a y there, which means the 6 goes there, right? Does that make sense? 2 to the y equals 6. We can put this in our calculators, and I'll show you how short. This is just pushing some buttons, and you get that answer. So do you see why this is useful? If we want to answer that question, we just rewrite it in the form of a log, push it in our calculator, and we got it. Okay?
So you just put in your calculator log 2 to 6.
Right, you do there is no log base 2 button on your calculator, but there's a really easy shortcut to show you how to do that. So just for now, just rest assured that I will show you how to push a couple buttons on your calculator and get that answer. I'm not gonna do it right this second, but I will. Okay? So, let's try some other ones real quick. How would we write the exponential form for this? 2 to the 4th equals 16, right? The base of the log to the other side equals 16, right? 4's got to be the exponent, 2's got to be the base, right? How about that?
10 to the 1 is 10.
10 to the 1 is 10. Makes sense, doesn't it? Okay. How about that?
2 to 0 is 1.
3 to the 0 equals 1. Okay.
10 to the negative 1 equals 1.
Equals 0.1, right?
What's the point of doing logarithmic? You just do mental math.
Okay, but okay, you're right. But what if? Okay, you can on those, but I defy you to do mental math on this one.
I've done it.
Seven to what power is 3? Come on now. See, it's a mental math book. See what I'm saying? That's pretty hard to do.
It's like,
You got it? Yeah.
that
Okay.
would be impossible, so, no.
So there's it's for the ones that you can't do mental math on that it's useful. Yeah.
That would be bad.
Okay, and like here's an example of one. Well, the one we started with, right? 2 to what power is 6? Well, it turns out, if you put it in the calculator, it's about 2.585. Okay? Strange, but that's how it works. Okay?
Do any of these decibels trivially for those?
Typically not. Yeah, typically not. Okay, so you guys, this is something you know how to, I mean, I'm going to kind of skip through this a little quicker. What's that answer?
So we're going 3 to what power is 1? So, it's, oh, no, it says 27.
4th. Good. And the way you know that quickly? Because it's 3 squared, right? 3 squared is 9, so that's to the 2 power. Square it again,
Right,
and that's the 4th power, right?
okay.
Okay? How about this one? Yeah.
If he was asking
Four.
for like
Three.
exact
Three.
answer,
Three.
which you just put in log 5.
Yeah, that is right, and that would be an exact answer. Now, what I'm going to ask you for is going to be a decimal approximation. So you'll be using your calculator. Okay.
3.
3. Everybody see that? Because 5 to what power is 125? 5 cubed. How about that one?
4.
4. Yep. Because 4 squared is 256. Okay, how about this one?
16.
To the negative 4?
So 2 to the what
Almost.
power is 132?
Negative 5. You see why? Why the negative? Just got to flip it, right? So 2 to the negative 5 is 1 over 2 to the 5th. 2 to the 5th is 32, so that's 1 over 32, right? Okay? All right. So we've already tried some. We're going to skip ahead. You guys know how to do this. Okay, here are some general forms. These make total sense. For you guys, this will be just a walk in the park here. Why is that true? Ignore this for a second. The base A log of 1 has to be 0. Why?
Because that's the one is equal
Anything
one.
to the 0 power is 1.
Because anything to the 0 power is 1. So A, whatever it is, A to the 0 has to equal 1.
Because anything is 0.
Right, so does that make sense? So anytime we take a log of 1, any base, the answer is always 0, right? Okay, how about this? Does this make sense? The base A log of A equals 1. Makes sense, right? Because we're saying A to the 1 equals A.
So
right?
Nothing happens.
So if you take a base A log of the base, it's always 1 for that reason.
Pretty obvious.
How about this one? The base A log of A to the x has to be x, right? Just think what that's saying. A to the x equals A to the x, right?
So that's pretty simple.
Okay? And what that's telling us, what we're going to get to soon, this is just an example of how taking logarithms and exponentiating are inverses of each other, and so they cancel each other out. Taking a base A log of a base A exponential cancels out. Vice versa is also true. Okay, and we'll see that. So natural logarithms. Natural logarithms, I'm not going to spend a lot of time on this because you'll spend so much time on this next year, and in calculus I will actually show you why E is such a special number. But we have to know a little calculus first. E is just a naturally occurring number. It's about 7128 or something like that. I don't even remember what it is. But it doesn't terminate, doesn't repeat. It's like pi in a sense. And there's a reason E is so special, but we'll get to that later. I could talk about it now, but it'll make a lot more sense when you know a little bit of calculus. We abbreviate that though. This is such a common, I shouldn't even use the word common. This is such a frequently used, you'll see why I shouldn't use the word common. Such a frequently used logarithm. It's used so often in biology and physics and chemistry for the reasons we'll talk about, in future years, that we give it its own name. So when you see ln, that's French for logarithm naturel or something like that, and it just means base E log. It implies that the base is E, but we don't want to write that every time because we use it so often that we just get lazy. We develop a shorthand. Okay, by the same token, a common log is one that uses base 10, which is hugely important to us because we have a base 10 number system, right? And so when a base 10 log, we just write as an log log, and if you don't see a base, what's implied? 10. Exactly. Okay. Okay, so where do you see these things? Well, on a calculator, this is an 83, but it's the same place on an 84. There's the base 10 log button, and there is the natural log button, or the base E log button. Okay? All right. So here's what I wanted to make sure I got to this. So the base B log of x is the inverse of the base B exponential function. Okay, this is really easy to show. Here's the easiest way, so they undo each other. The easiest way to think about this, I think this is in the PowerPoint. So if I ever take the base B log of a base B exponential, they cancel out and I just get x. If I ever raise a base B log, if I ever raise B to the power of a base B log, does that make sense? So I'm taking a base B exponential of a base B log. They also cancel out and just leave me with an x because they're inverses, right? That's useful. We'll get into that more and more. The reason this is true, that they're inverses, okay, is because, and here's just a couple examples, right? I'm taking 10 to the base 10 log of something, so they cancel, right? I just get 2. If I take a base 3 log of, now this doesn't look like an example of that, but it is. 9 to the x can be written in terms of a base 3, can't it? Everybody see that? Right, and that's something that we kind of dealt with in chapter 7 a little bit. How could I rewrite 9 to the x in terms of 3? 9 to the x equals yellow. Equals, what's 9?
3 squared.
3 squared.
3 squared per x.
So that's 3 to what power? 2x. Right? So I could rewrite this as the base 3 log of 3 to the 2x. So what, right? That cancels that, and my answer is 2x. Okay? Right?
So
Logs
if you had to
and
replace-
exponentials undo each other. Okay? A very special relationship we use a lot in math.
But isn't the 2x like an exponent? Or?
Well, it is, but remember that logs, think what this is really saying. If you look at this expression here, it's saying 3 to what power is 3 to the 2x?
Oh, okay.
Right? Does that make sense?
Yeah.
But you can also just think about it algebraically as the base 3 logarithm as canceling out the base 3 exponential function. Just like a cube function would cancel out a cube root. Okay, same kind of thing. Okay, so another way to look at these as being inverses is, okay, I'm just going to show you. I don't know when they do this, but watch this. If we start off, let's say, with a logarithmic function, if we take the function, so we're starting off with y equals the base b log of x. What's our recipe for finding an inverse? Switch x and y, right? So we'll switch x and y, and we get the base b log of y equals x. Okay, all I have to do now is rewrite that as an exponential function. What is that as an exponential function?
B to the x equals 1.
Y equals the base of the logarithm becomes the base of the exponential. A log is an exponent, so the x is the exponent. Voila, they're inverses. The base b log of x is the inverse of the base b exponential of x, right? It's easy to prove.
Yeah, easy.
Okay? Just by following our formula. So find the inverse of that for me, please. How would we do that?
Log switch x.
We really just know the answer. Just tell me the answer first without even thinking about it.
X,
3 to the x, right? The inverse of a base 3 logarithm must be a base 3 exponential. So we know the answer right away. We know that it's going to be y equals 3 to the x. How could we prove that? Like I just said, we'll just flip the x's and the y's and get the base 3 log of y equals x and rewrite it as an exponential. Gives us the same thing, doesn't it?
Yeah.
Okay, take your pick. You guys are smart enough to just do that, though. Okay. So that's another thing I'm going to have you do is write inverses. Okay. Okay. So wait, there's a good one. Let's do this one. Yeah, let me go back a little bit. Forgot about this one. So find the inverse of this. Just tell me the answer first. Well, actually, maybe you can't on this one. It's a little trickier. We really have to probably rewrite this one, right?
What's the
E
L?
to the x plus 1.
Remember, that's the base e logarithm. So all that means, when you see an ln, that means a log base e, right?
So it's just e to the x plus 1, right?
Okay, so then this would be like saying y plus 1 equals log x, right? But let's just show this. If we just flip the x and the y and solve, that's how we always find an inverse, correct? So if we exchange the x and the y, we get the base e log of y plus 1 equals x. How do I rewrite that in exponential form?
E to the x equals 1.
Yeah. Right? Does everybody see that? Everybody see that? You guys getting this? Okay, so we rewrite that as y plus 1 equals the base to the x. So what do I do to solve for y? Subtract 1.
Right, so you just have y equals e to the x minus 1.
Okay.
Which is k.
Okay, now here's kind of a shortcut. We could do this algebraically. There's two equivalent, and you guys are getting to a point now, you're getting to the tipping point in math, where math gets so cool. I mean, you can start to see that all these multiple ways of looking at stuff are just different models that represent the same thing. We could do this like we did by just trading the x and y and rewriting this as an exponential form. But we can also algebraically, what's our way of undoing a base e logarithm? Yeah, base e exponential, right? So I could do this. I could literally take each side, I could raise e to the power of each side, right? I'm taking a base e exponential of each side. What is a base e exponential of a base e logarithm? Cancel, right? Because they're inverses. Those cancel. And I end up getting y plus 1 equals e to the x. Same answer. Right? Isn't that cool? I just think that is so cool. I see this every year, but I just really think this is a cool point when you get to see this. Okay? Okay. Switch the x and the y, and they just wrote it in exponential form, but I just showed you the way you can just use algebra to do that too. Okay? We already did, graphs of logs. Simple. Okay, so graph of a log, we'll make this really quick. I'm not going to focus on this as much. If the graph of well, I'm just gonna do this on my own. What do you think the graph of a log function looks like if it's the inverse of an exponential function?
The collection thickness of it, whatever, what's that called?
To the K.
Right, so let's graph on the one hand, let's graph the function y equals, let's just do b to the x, how about, right? So it goes through the point 1, y-intercept is 1, because a is 1, right?
We have like 3 minutes.
That's all we need, okay? Well, to get the inverse, we do one of two things, right? We either just reflect over the line y equals x, or use my trick, we rotate 90 degrees and then reflect over the y-axis. Okay, either way, do you see that you're just gonna get this?
Oh wait, what is that? Oh, okay.
That's a log. This is the graph of y equals the base b, the base b log of x. What are the characteristics of that? It's got an x-intercept of 1, okay? And it increases very rapidly to the left of that, but it slows down, becomes a ploddingly slow function after a while, right? It just really flattens out. The exponential function has an asymptote that is the x-axis. The log function has a vertical asymptote that's the y-axis. Okay? So that's the graph of a log function. The easy way to remember it is, it's just the reflection of an exponential function over this line because they're inverses. Okay? All right. So, I think. Okay, good. So let me just, I want to get as far as I can through this. I want to just introduce you to a couple quick things.
1 minute.
And we won't get super far with this, but we'll get as far as we can. 1 minute's fine. I'll just show you a couple properties. Okay, properties of logarithms. Here's what I wanted to show you about making things easier. Now watch this. The logarithm of a product, look what it does, becomes the sum of the separate logs. So if I do a base b log of the product, oh well, we'll hit this. Okay, we'll probably hit this Monday, and then that'll be our last day in class.
I was totally
Ever.
lost.